Hi everyone, my name is Denise. I'm a PhD candidate at the University of Pittsburgh. I am in the Intelligent Systems program, and my research focuses on modeling student behavior, and they're using any kind of educational technologies.
And I am Dr. Cassandra Kelly, a Broader Impacts Project Coordinator at the University of Pittsburgh. We'll talk more about broader impacts. If you attended our previous workshop, some of it will sound a little familiar, and we'll explain the purpose of our workshop is today, but our focus is on research with neuroimaging and educational data mining. And part of our collaboration is with CIRCLS. So if you're not familiar with CIRCLS, it's funded by the National Science Foundation to support NSF awarded projects in the Research on Emerging Technologies for Teaching and Learning, or the RETL program. And so CIRCLS stands for the Center for Integrative Research in Computing and Learning Sciences. And our community consists of researchers, emerging scholars, and educators. So Educator CIRCLS is one of the sub-communities, and our main goal is bridging research and practice, which is what this workshop is all about. So our Teachable Robots workshop was the first one we had in this series, and some of the information framing this will sound familiar if you did attend that. They're two different research focuses, but the idea behind them is very similar. So I mentioned I'm a Broader Impacts Project Coordinator. What does that mean exactly? Broader Impacts is part of the NSF grant. So one of the goals of Broader Impacts is to make a societal impact with the research and to impact not only those who are part of the research, but also others around. In education, that might mean the teachers, the students, and thinking about ways that we can bring it to practice. So today's session is going to be thinking about what are ways that we can make the research more accessible to educators. And specifically, we're looking at this field of computer science. So one aspect of broader impact work is educational outreach, which can focus on professional learning for educators, but it can also be directly impacting students with instruction. And the goal is to broaden participation of underrepresented populations by introducing students to the concepts and engaging them in this space so that they'll continue to work in these fields. So our goals are to share the concepts and the research. We also wanted to give you something tangible to take back into the school and classroom. So in this particular study, we're going to talk about neuroimaging equipment, and that's very expensive. It's not accessible to everyone, and we recognize that. There'd also be a need for further support and training if educators actually had this equipment, right? So we wanted to think about another way that we can bring elements of the research to you without necessarily having the technology. And then the last piece is that we did a phase 1 of our study where we interviewed teachers ranging from preschool to high school, all about their experiences with professional learning with STEM and computer science education and the impact that that's had on their practice. And we are bringing in recommendations from them into how we've set up today's workshop. So we have two goals of our workshop. Number one, obviously, professional learning about the research and what's happening in this space. But additionally, we really want to collaborate with you and get your thoughts about where the research can go next and how it might impact your practice. And we're really hoping to learn something from you because we've designed this with educators in mind, specifically thinking about ways that we are bridging research and practice. So remember today that we're going to ask you wearing both a teacher hat and a learner hat, thinking about it from the professional learning standpoint, as well as if you were to bring back elements of this into your classroom. And then I wanted to preface that I am not one of the researchers on this particular study, but Denise is, and she works alongside other faculty from various institutions. And so that team is the one who's behind the actual research for neuroimaging and educational data mining. And for me specifically, I'm looking more at the broader impact of reaching what Denise is doing with her research team into classrooms and schools. And it's inspired by work with intelligent tutoring systems and educational data mining. Before we go further into the project and the activities, we wanted to just take a moment and reflect on our vision for learning and to see what kind of reactions you might have to this question and this image. Is this the vision of learning that we want? Seeing some really comments in the chat. I want more than this in my classroom, or not in isolation because we need students talking to each other. speaking aloud in different languages, academic, conversational English. Thank you all. It's so nice to hear that we all seem to have a similar agreement about what learning is and how we might define it and how it can be observed in different ways. So it's not necessarily learning in solitude, right? Because we can't see what's happening behind the computer within the technology space of it, recognizing the importance of social learning theory and interaction. And so today we're going to be thinking a lot about what happens in the heads of students as they're learning and making connections across learning science and neuroscience. But we do want to acknowledge that there's lots of different aspects of learning that are important to consider.
So, as part of our workshop today, we are going to be talking about terminology or some CS concepts. So, we have a list of them on the screen. These are the terms that will be referenced throughout our presentation. We don't expect you to be familiar with them, but we included definitions in the notes that you can use to help with your understanding. We start off by talking more about learning sciences. So basically, this field focuses on understanding how people learn and design educational innovations to improve learning outcomes. It draws from multiple disciplines like psychology, education, computer science, and maybe more. And throughout this workshop, we'll explore how these connections enhance our ability to create engaging and effective learning experiences. But a really specific contribution to learning sciences from computer science is the intelligent tutoring systems. An intelligent tutoring system is a computer system or a program designed to provide personalized instruction and feedback to the students. These systems use artificial intelligence to adapt to the individual needs of each learner. For example, matching the appropriate learning level or adapting the difficulty of the tasks, providing instant feedback, offering hints, or providing explanations and other engagement or motivation strategies. Some of them even support other forms of learning, like in the discussion, like more collaborative approaches. So it has all kinds of different sorts. So these kind of systems collect a lot of data from the students. So these capabilities of these systems rely on the data that they collect during students' interaction with them. And these kind of data basically include the clickstream data, like what the student actually clicks on when they're using the system, the time spent on certain elements, also performance data such as the number of attempts or number of hint requests, and the errors that they make. So we talked about how intelligent tutoring systems collect big amounts of data on students' learning experiences. Now I would like to talk about how this data is used for making inference about students' learning. We usually refer to these kinds of efforts as educational data mining. It is a field that involves analyzing educational data to uncover patterns, insights, and trends that can inform and improve teaching and learning practices. The insights that we gain from methods are actually what makes the personalization in intelligent tutoring systems possible, or we can even say that it is what makes these systems intelligent. It can also help teachers by providing diagnostic data on students' learning and maybe identify like who's doing well or like who's at risk. And it also has some benefits to the researchers to like develop new educational tools based on the insights that we get from these sorts of data analysis efforts. For example, data on student interactions can guide the design of more effective intelligent tutoring systems and adaptive learning platforms. And another way it supports research is that it can also generate evidence-based recommendations for educational policies and practices. So I'll hand it over to Cassandra.
So the idea behind these workshops that we've been putting together are to have guided learning activities where you get to experience the role of a researcher and have an opportunity to gain a better understanding of some of the computer science concepts that were applied within the research methods and findings. We did keep in mind both the AI K-12 initiative, the 5 big ideas in AI, as well as the K-12 computer science framework, and trying to think about ways that it can integrate potentially within other subject areas. So for example, in the K-12 computer science framework is visualization and transformation, which is all about organizing, clustering, and categorization of data subsets. And that's what Denise was referring to before about educational data mining. And so we're going to be thinking about that and how that might include visualizations like graphs and charts and infographics and ratios. So just want to remind you that the activities are intended to be thought about integration with students, but they also could be for other teachers' professional learning if they don't have a computer science background or they're just getting into this area of computer science. We also have considered the ISTE standards for educators and students, thinking about where they might fit in as well with some of these activities. So we have two breakouts that we're planning for today. One has to do with educational data mining and visualizations. And then we're going to come back and talk about the neuroscience aspects of the research and activity two, the brain activation sort. The idea is for you to think about the design of intelligent tutoring systems and understand the types of data that's collected, in addition to being able to actually analyze it. But we also will explore other forms of data mining to better understanding how learning might occur when students interact with these systems. We're going to go through the activities as if you are the learner. I'm going to prompt you to make your own copy with all of the instructions so you can do what you want with the copy of it. We're also using a free educational software today that's for online data analysis. It's called CodeApp. It's a great free tool that you could actually do other things with in the classroom. So that's why we selected it. And we're going to specifically be using it to do some practice with creating educational data mining visualizations. And again, this might sound completely abstract to you, or it could sound totally comfortable, but that's the idea here is we're trying to use an inquiry model to just get you thinking about it, and then we will frame it and explain how it connects with our research. There's two parts of the activity. So the first one is using CodeApp and the data that's on there. And then the second step is we have some questions where you're looking at correlations with an altered data set. So you're doing some experimenting with the data that we provided for you. And then after you go through that, there's some questions to talk about within that document. You might start to get a sense of what it's like from the student perspective, and you might want to talk higher level, wearing your teacher hat. So these are some questions here that if you finish early or you just want to talk more in depth about the actual behind the scenes of these activities, you can reference this slide. We appreciate you taking time to speak about the activities and just some of your experiences.
A recent work that I've been involved in was also looking into the level of autonomy or like agency that these systems give to students and how that influences learning. And it's also a part of making these systems transparent to the users. So it is definitely like an area of research within educational technology or like intelligent tutoring systems to make products more transparent.
I heard my group talking about where rote memorization is applicable versus other modalities of learning. And the conversation was leading to that there's a place for both, and everyone might process that in different ways. So for this activity, the data was showing you a lot of differences in how the students do respond and the amount of time taken. And the way I was looking at it with my teacher hat was like, wow, if only I could have had this technology when I was in the classroom, when I had so many diverse needs going on. Even at that time, like there's some elements, like obviously with standardized testing and whatnot, where they're already classifying students. And I didn't like that aspect of it. But what could be powerful is how some of that data can adapt in real time and make some of those changes that I couldn't do as a teacher for many students. So I think that's where maybe we can see some real power in this. And our activity was meant to both give that conversation point, to get you thinking about it, but also so you could experiment if you were a student manipulating the data to see what it really means and that transparency. So it's awesome to hear you got to those points. And we'll talk more about these other reflection questions when we reflect overall on the workshop. So let's let Denise take over to our next point.
Thank you. Yes. So you all have looked at a sample data from an intelligent tutoring system, and that was like the interaction log data that is usually stored in textual format. So we also talked about like how these systems collect this data, how this data is used and analyzed. You did it yourself a little bit. But the challenge there is that we assume students are going to be engaged all the time and provide this data continuously when they're using these systems. So unfortunately, this is not always the case. And if the students become idle or if they stop during their interaction with the systems, all the data that we can get is just the duration of that pause. So in that case, it's merely impossible to build a model of their behavior because there's no behavior being logged there. So the main question of this project that we're talking about in this workshop today is what could we do if we could add the brain data as another sensing technology that allows us to understand the student's internal experience. Brain data could theoretically provide an additional signal of states, like whether someone has mastered a concept or whether someone is focusing or distracted, without relying on explicit input from the user, because it's in continuous form. It's not in lapses like the textual data that we get from the systems. So these signals might change from moment to moment and potentially be more fine-grained than the other types of sensing. For example, we might be able to determine within seconds the moment a student has an insight when solving a problem. And this could allow us to be even more accurate in our ability to provide intelligent support for students and provide actionable information for teachers. This may seem far-fetched now, but as brain sensing technologies are becoming more portable and affordable, it's likely at some point in the near future that might be feasible. And so we have a video that is showing what FNIRS looks like. This is the technology that we're using in our experiments. And I would just like to play the video for you, and I will be explaining some of the things that are going on in the video as we watch it. So basically, it has multiple sensors, and some of them will emit light, and some of them will be detecting light. It's a non-invasive brain imaging technology that measures brain activity by detecting changes in blood flow, uses near-infrared light to monitor oxygen levels in the brain, providing insights into which regions are active during specific tasks. So it comes with its own software. You set it up the way you like based on the area of the brain that you're interested in, based on the task that you're giving to your participants, and you assemble it as you're seeing in the video based on the design that you choose, and then have your participant wear it as you see in the video. There are some steps to adjust the signal that you're getting once the participant wears it. And then once the signal quality is good, now it's showing you that how they assess the quality of the signal from all the sensors. Once it's acceptable, you can proceed with your experiment, whatever experiment you like. So in this video specifically, they're looking into finger tapping experiment and just like looking at the difference between in the controlled state, and that's just doing nothing in this experiment, and right finger tapping and left finger tapping, and basically looking at how the signal changes. The software that comes on the cap, just like installing the sensors with this device, allows you to look at the changes in real time, like look at the signal in real time, and you should be able to see peaks of activation when the participant is doing or like performing the tasks that you give them. This is really suitable for learning experiments because it's portable and light. You can even walk with it, put the device itself that connects to your laptop. You can put it on a backpack and actually walk with it too. So like it's that light and it's portable. So this is one of the common ones that is being used in learning experiments. There are open source platforms where you can analyze FNIRS data. For example, there's a toolbox that you can download on MATLAB, on top of your MATLAB, and you could just proceed to analyze this kind of data if the data is shared publicly. That's like another issue with this kind of data, because some institutions consider this kind of data as identifiable. So some institutions see it as like sensitive data, so it's kind of like a pain to share it online, but there are online tools for publicly available data to analyze. This is still really like novel technology. Using brain sensing and within learning sciences is, I think, pretty new and recent. We can start to take a look at some examples that we have from the literature. I'll hand it over to Cassandra for now.
So here we see some visualizations of brain data that was collected using FNIRS while people were performing different tasks. So you can see in the images the different parts of the brain that were activated. And this research has been done in military training and in flight simulations to offer insights into how the brain responds to stressful situations. So this one's showing table tennis, piano, playing the violin. So you can get an idea of what parts of the brain are activated. And so our next activity that we thought would be interesting for you, this is not from our research specifically, but it's just to give you a sense of how to identify what parts of the brain are activated and what it could mean. So we have on that same, the guided activities sheet, we have 3 images of the brain. And they show activation in the brain while completing different tasks of varying difficulty. And so we wanted you to take a minute and analyze which would be the high level or middle difficulty and low difficulty tasks, and to just take a minute and think about how this might be impactful in the classroom. See, this is why you all were invited here, because I love getting new perspectives and thinking about it in regard to like motivation and mindset and other ways that we can really get students engaged. And also from a teacher hat, just this whole idea of neuroscience and learning sciences, I feel like we never talk about it. It's always psychology based. There could be some relevance, especially when I think about some of my students, like we talked about the IEP students that had legitimate things happening where they were thinking about something else, and to be able to zone into where they were thinking or what part of the brain was activated and maybe find a way to help them, I feel like would be an incredible tool. But it also, as Denise mentioned, could be very invasive. And so we're going to talk a little more about some of the implications that could come with this work. And obviously it's not precise, right? So it's not as easy for us to just tell. And it changes, as Denise said, like it's constantly changing as you're actually interacting and wearing it. So it's not as simple as just identifying these images and knowing exactly what it means. And I'm going to let Denise talk to you a little bit more about other research in this field.
Let's take a look at a few more examples of using this kind of data in the literature, seeing some early promise in using brain data to understand cognition, attention, and emotion during learning. For example, in this figure, this is from Spuler, they link cognitive workload to task difficulty, which is something a few researchers have worked on. Spuler used this information to build a proof of concept interface that adjusted problem difficulty based on the workload detection. But being it in the proof of concept stage is really important. I would tell you to remember that. And another example is from Safir and Mutlu. They actually have an attention-aware interface where they infer students' attention during particular instructional videos using EEG. And then in a proof of concept, prompt students to review the videos where they had low attention. And so, like the both examples that I showed you were in the proof of concept stage, meaning that they're not in the full application yet. We haven't seen a lot of movement beyond the proof of concept stage because this kind of work is very challenging because the real world contexts are where learning occurs is really noisy. As students are trying to learn something, they experience several intersecting learning processes like cognitive, attentional, affective, motivational. But they may be learning through different activities and modalities. For example, it's very different solving a problem on pen and paper compared to talking about a problem with another student. And then trying to model learning processes using brain data, researchers contend with substantial variations in the brain signal. It could be between different individuals, like it looks really different when you compare one student to another, but sometimes you see big differences within the same individual across different sessions too. So it is a really challenging data format to parse and analyze. But there are some steps that we can take toward using brain data to support learning. We know a lot about how low-level cognitive processes like attention affect brain activity in controlled lab settings, like tasks in the psychology experiments. So I was talking about this in one of the breakout rooms that I attended. When you attend psychology experiments, for example, attention tasks, and if you think about those tasks, they are really isolated. They're like really strict to isolate a specific form of cognitive activity. So in those kind of activities, it's easier to isolate a signal and understand what that means in reality. reality. So, but we don't know how these processes play out in real learning environments, or if models built from these like controlled artificial tasks can be applied to real world learning settings. For example, this is from our own work. In the figure on the left, we show that we can distinguish between proactive mode of cognitive control, where a person is actively maintaining a goal in their mind, and the reactive mode of cognitive control, and that is just responding to what you see on the screen. This is using a control task, not a real problem-solving activity. This distinction could be useful for learning environments because proactive control may relate to self-regulated learning, where a student is planning and working toward problem-solving goal. And to explore this, we try to encourage students to use proactive control while solving math problems. So transitioning from this really artificial task to something that we could see in real life, like in a problem-solving experiment in the right panel of the figure. We can define when students are in proactive or reactive states in real-world learning scenario and use brain data to detect these states based on what we know from control tasks. So our hope is that this research can help us apply what we learned from the brain and control settings to more complex real-world learning tasks. But the biggest challenge with this kind of work, I would say, is translating what you know from this like really artificial task that is easier to isolate specific cognitive processing to something really noisy and complex like problem solving. And our work is so far was mainly looking into how we can translate these cognitive states as they're defined in cognitive neuroscience within a realistic environment. And the next step is going to be having it all together and looking at signal data when people are doing real learning tasks. And our findings so far, we have been looking at two different kinds of cognitive mechanisms, cognitive control and learning. We found that we can elicit behaviors related to different modes of cognitive control. That was the work that I showed earlier in the previous slide. And phases of rule learning, and that was the data that you looked at in activity 1, through prompting and realistic problem-solving scenarios. This was the intermediate step that we took to being able to understand the signal that we get from the device. Like, do these mechanisms look like in a behavioral setting, in the data that you collect? And we are able to model the different phases of rule learning using the data collected from the tutoring system. We are able to give fairly accurate predictions of different phases of rule learning in the data that you looked at. And we saw that these models can transfer across different tasks. Like, we actually tested this on an artificial task, and we saw that we could transfer our predictions from one version of a task to another. But there are still some challenges in detecting some of the states. For example, when a student is in a misconception state, we can't really give a prediction better than 60% accuracy for that kind of a state. So we're in the process of integrating brain data into this analysis to see if we can actually get better predictions if we included this sort of like signal data. If signal data could disambiguate some of the harder to detect cognitive states occur during learning. And we're also looking at if we can make the AI models that we're building generalizable to settings that does not have the brain data at all. We learn something from using both the brain data and the behavioral data from the tutoring system and generalize that kind of model to a setting where the only available data that you have is the behavioral one.
So if you're like me, your head spins at just thinking about all of this, and it's mind-blowing, pun intended. I was really intrigued by this study, and this is actually a little bit of a dated study. 2018 is not as current with how the technology is evolving, but it was done by Holstein et al., so not our research team. And if you look at the pictures, it's crazy to imagine that this could be the future where teachers could have students working through an assessment and in real time see what their cognitive states are. So in this picture, it shows that the teacher had this mixed reality smart glasses that were co-designed with middle school mathematics teachers. And it was designed so that it would be this method called co-orchestration between the human teacher and an AI tutor. And that way it would notify the teacher where a student was having challenges, or a student was off task, or a student was gaming the system. And so we wanted you to really think about this possibility of the future, this level of support that could happen, especially when you think about this MRI equipment in the hospital, how massive it is, and now how portable this FNIRS device is, right? So we can only begin to imagine what these devices could be like in the future. And we've also discussed the importance of where does this fit in, because because there's also the concern, do we really want students connected to brain devices and computers all day? Is that the type of learning that we want? And I think we all know that that's not the case, right? Thinking about just the pandemic and all the challenges that we faced when we didn't have that human connection. So we don't want to stray down the pathway towards this overemphasis of data collection. But could there be ways that we could identify students' learning and metacognitive and behavioral states in real time and maybe use this to support them further and customize their learning experiences? So we wanted you to take a moment and reflect on what other superpowers would educators like yourself want in the classroom using some of these types of technologies. That was the first thing that came to mind when I started to learn about Denise's work, is I thought about all the students that I was really trying to help and how to understand where to help them. I also have a friend who, this is just a little aside story, she's a former teacher and her son has been having a lot of challenges with focus and behavior, and they ended up doing some brain testing, but it was looking more at his sleeping patterns. And they found that when he was sleeping, if he wasn't getting into the REM portion of sleep to where his brain wasn't recharging enough, and it was causing all these behavioral things to happen. So I just thought, wow, I can see as a parent, as a teacher, just to be able to identify what's happening with the activation of parts of the brain being a really powerful tool when we're talking about learning. Why aren't we talking about the brain? There really seems to be a connection that's important here that's not happening as much in education. We're focused more, like I said earlier, on the psychology. So I definitely could see that being something interesting. On the flip side of the coin, we also have these concerns about surveillance, data. A lot of you have alluded to this. And is this the vision of AI we want? If we had more time, we would continue with all the activities because we had other things in mind. So in your handout with all the activities, we're calling them extensions, that if you were bringing this back to share with other educators or potentially with students, that you might adapt in some way. So one of them was specifically about how to code an intelligent tutoring system and thinking about the language that's used for feedback and scaffolding, but also how students might be thinking about how to communicate something if they were giving feedback to one another on math problem solving. It doesn't have to be in the context of math, but that's just the examples that align with what Denise's research was looking at here. This is also helpful to think about ways that misconceptions could be identified and how a teacher could scaffold instruction based on what the system does. So that's just there as something that you could remix and adapt. And then on the next slide, this was something that I thought was interesting. So on the left is a book that I highly recommend if you haven't read it. It's called Urban Myths, and it talks a lot about all these myths we hear about in education and how they've been debunked. Like there wasn't a lot of research behind them, and we were told it and sold like, hey, multiple intelligences, here's the thing, or left brain, right brain. And now that there's been more research, they've actually found that some of it's not accurate. So I had created a quizzes for us if we had time. And so this is something fun you could do later just to test your own knowledge and again, to share with others. I remixed it from quizzes and I brought in a lot of questions that were specifically from that book. Please be sure to play if you have time, or at least look at the questions and think about how that's impacted your own practice with a lot of that misinformation that we've been told. And then we're going to move into our closing discussion. So just to give you a full picture one more time, this workshop was designed to teach you about the research that was happening from a professional learning standpoint, but it was also to share some of the content behind the research and give you the experience of the researcher, as well as thinking about could these activities be brought into the classroom and adapted in some way. This model of sharing research with educators in a way that tries to make it more accessible, not a bunch of jargon and complicated terms, without actually applying it in some way in an activity. Thank you again for all the insightful contributions. We really appreciate the opportunity to reflect on this and thinking about it from, again, the teacher perspective, as well as what our students need and how their students would be impacted by these things, and the misinformation that can come from these technologies, as well as some of the benefits that maybe they could offer to support educators. We had a series of sessions this summer and the summer before, and several of them were looking at ethical and equitable issues with AI. So there's some great resources. Please be sure to check those out. And I do want to acknowledge our research team. This work wouldn't be possible without all of these people who've been working on the research projects over the years that we've presented to you today. And on our next slide are some of those publications that have come from this work. And you're welcome to take the presentation slides and all the resources and share them with other educators. That's our whole purpose of this. And thank you so much for being here today. We truly appreciate it.